Okay, now we're going to look at a very important equation, but a simplified version. The equation is the continuity equation. So the continuity equation is about conservation of some quantity, like energy or charge, and is in fact the foundation of some very celebrated equations, such as the convection diffusion equation, Boltzmann transport equation, and the Navier-Stokes equation. So the Boltzmann transport equation is very important in semiconductor science. And essentially can be used to describe all flow of charge, holes and electrons and so on in a semiconductor. Navier-Stokes is to do with fluid flow, mass transport of fluids, whether they're incompressible or compressible. So the continuity equation is based on a conservation law, and essentially it means we have a flow of something, and if we look at a particular area, what flows into that area must also leave that area unless there is a source or a sink in that region. Now, a source is a place where the items, for example, energy or mass, is generated, and a sink is where the energy or mass can disappear. Now, we're interested in actually charge, and charges cannot be created nor destroyed. But in a semiconductor, we have electrons and holes that represent charge, and when they combine, then essentially the charge doesn't disappear, but as far as the free carriers are concerned that can provide current, they disappear. So in this case, the currents that we're interested in are not conserved, and so we need to put in place source, which is a generation term, and a sink, which is a recombination term. So before we can go and look at this continuity equation, we need to look at what concept of flux. Now, flux is to do with the flow of something, and in our case, it's the flow of charge, and we're talking about current density. The current density is the current. This is the current, which is measured in amps, and this is the area, cross-sectional area. And we're interested in the cross-sectional area that is at right angles to the direction of flow. So we know that this flux has a direction, and hence it is a vector. So if I draw some lines which are supposed to represent the flux, we can have a flux that does something like this. So we usually represent it by these lines. And in this case, it will be a movement of charge. And what we're looking at is some cross-sectional area at right angles to these flux lines. And we're looking at the amount of that material that flows through that area per unit time. Now, in our case, we are interested in electrons and holes. So we talk about a flux of holes, Jp, and we talk about a flux of electrons. And the total current, which will be made up of the electrons and holes that are free to move, essentially because they have opposite charges, then the total current will be the difference of these two fluxes. Jp is positive charge and Jn is a negative charge. And essentially, when we deal with current, we're talking about, in conventional terms, we're talking about positive charge movement. So let's consider situations shown here in this figure, figure 1. So we have our flux of charge coming from the left. And so we have flux coming this way, and there's a certain amount of flux coming out. So If there is no disappearance of flux in the box, or no generation of charge, or in this case charge in the box, then what comes in should also come out. But it's possible in our case to have generation and recombination. So we need to look at these two cases. So what we're going to do is represent, put some dimensions on our box. So we start off at x here and move to x plus dx. And we have a flux, we're just going to look at the holes. And we can look at the holes independent of the electrons, because when we have recombination or generation, they're always equal. So if we have recombination electron and a hole, then both electron and a hole are involved. We have generation, again, electron and a hole are involved. So we can treat these two fluxes as being independent, in the sense that there is a continuity or conservation for both of them. So we have a flux of holes coming from the left, and we call that F of P at X. And then we have a flux of holes coming out of our box at X plus dx. And if there's a difference between these two fluxes, then there must be either charge created, or in this case, holes created or destroyed within the box. And they get created by generation and they get destroyed by recombination. So we can write down the change in the density of holes. So the P stands for density of holes. In the box. So the rate of change of the density of holes in our box depends on the difference between what goes in, Jp, and what comes out. So if more comes out, that means we have generation. So this term will be positive. If less comes out, then we'll have recombination. dy dz, clearly that's our cross-sectional area. And if we want to write this in terms of the rate of change of the current density, so the derivative of Jp, we just add a dx here, we get the volume of our box, so this is the volume. And so now we have an equation that equates the rate of generation of holes inside the box to the rate of change of the hole flux density. Now, we can equate these two. Essentially, we have a generation term, and we have a recombination term. And in steady state, we expect there should be no change in the population of the holes inside our box. And steady state basically means that nothing changes with time. So in steady state, our term, the rate of change of the hole density in the box with time, should go to 0. And the reason it goes to 0 is there will be a balance between the rate of generation and recombination in comparison to the differences in the flow. Now you might recall that when we looked at the total hole current, it was made up of a drift current term and Sorry, I've got that the other way around. This is a diffusion current term, and this is our drift current. So the total current is made up of both diffusion and drift, so we can substitute that back into our continuity equation, and we get a second order equation which relates the population of the holes to the generation and recombination. So this is our equation that will tell us how things change inside our semiconductor for the holes, taking into account flow of holes and generation and recombination. And we can write a similar equation for the electrons, but notice the sign change when we talk about the diffusion. Both the generation terms and the recombination terms are the same sign and the same rates, because for the electron there is a hole generated or recombined. If we get rid of the electric field intensity, so we say there's no electric field, meaning that we can get rid of this term here, that then leads to this equation, which is known as Fick's second law of diffusion. So let's have a look at a scenario where we can apply the second law of diffusion. So we're going to have some species at some location. So we're going to look at, maybe one example is we can have a jar full of water and we drop in this water some ink. And then the carbon particles within the ink will start to move away, and we can use this equation to describe how they will move with time. So we have time on this side, and we have space on this side. And the solution to that equation is this equation. So again, we have a function of time, appearing both here and here. And it's also a function of space. So if we show diagrammatically what this function looks like, it looks like this. So this is where we dropped in the ink. So this is where we have the time t equals 0. We put a spike of something. So we put in a spike of some species. In this case, the species is J. And then we can see what happens with distance. So along the horizontal axis, we have distance. And then we can look how the situation changes with time. So we have various time states. So initially, this impulse will start to spread out very rapidly because there is a very sharp change in the population. Initially, there's none of it here, but there's a lot of it here. And so the rate of diffusion will be very high. So initially, very rapid movement away from the source, the epicenter of this introduction of the species. As time goes by, then we'll get a spreading of the species. In our case, ink will start to spread across like this. And again, as time continues to go by, then the population at this epicenter will decrease and we'll get more and more of the ink moving away from the center. Time progresses further, it gets further and further away. And the source strength at the origin starts to drop. And what we noticed, though, is initially there was a very sharp change, and so diffusion was very rapid. When we get over to here, we see that the diffusion is slow because there is a very gentle change in the population. When we looked at here, the origin, the diffusion is rapid because there is a large change in the population. Well, let's look at a real-life example. Let's look at the introduction of our carbon particles in the form of ink. And we ask the question, how long will it take for a carbon particle to reach 50 micrometers away from the epicenter where we drop the ink in? And we can substitute it into our equation and find the result. And I won't go through that now, but the result is it takes just over half a second for a carbon particle to move away 50 micrometers from the original source of carbon. However, if we ask the question, how long will it take for the carbon particle to move 1 meter away? So now we look at how long it will take to go 1 meter away. It takes approximately 8 years. So we see that fusion is a very short range or local effect. And this is an important observation. Now, this diffusion, you might expect, depends on the diffusivity of the, or viscosity of the material. And so if we don't use water, we use something like oil or honey, then we expect that the rate of diffusion would be even less. This is true, and this relationship was in fact derived by Einstein. And also a very celebrated equation, where B is the diffusion constant, B is the viscosity, K is Boltzmann's constant, and T is the absolute temperature. But in the semiconductor devices and electronic conduction, mobility is comparable to viscosity. And we can sort of define a viscosity for electrons to be mobility divided by fundamental charge. Well, let's now consider a different situation. Let's consider diffusion in air at room temperature, or 20 degrees. And we look at some various gases. So the diffusion coefficient for carbon dioxide is this. For water vapor is this. And for oxygen is this. So we see that gases, in fact, diffuse much more rapidly than they do, much more rapidly in air or in gas than they do in a liquid. When we compare the movement diffusion coefficient of carbon dioxide in air and water, we see that there are nearly 4 orders of magnitude difference in the diffusion coefficient. So it will take approximately 3 minutes for the population to move about 1 meter, carbon dioxide population to move 1 meter from the epicenter for carbon dioxide in air. The diffusion coefficient is also a function of temperature and pressure. And we find that diffusion is more rapid at high altitude. And it's interesting to think why that should be. And I leave that for you to think about. And the temperature relationship is given by this. And we can run experiments to work out what these forms are. I'm not going to worry about that. We look at diffusion in solids. It's much more complicated than the above, but the ideas are very useful. So the diffusion coefficient for electrons in silicon is 35 by 10 to the minus 4 meters squared per second. With holes, it's 12.4, and half as much at room temperature. So we see that the electron gas in silicon diffuses even faster than most gases in air. Again, an interesting observation. So that's it for the continuity equation. We'll be looking at other examples of using the continuity equation in the next sections.